if you'd like to know why the geometric mean theorem is true, there's a couple of different visualizations that help it make sense. I'm going to focus on some properties that are true for every right triangle. So first, what is the geometric mean? The geometric mean of 4 and 9 is the number 6. Why? Well, they form 3 consecutive terms of a geometric sequence. What's a geometric sequence? Well, a geometric sequence has a common product. In other words, if I multiply 4 by a number, then I'll get 6, and then I multiply 6 by that same number and I'll get 9. And what's that number? The number is 3 halves, right? 1.5. If I take 1.5 times 4, I get 6. If I take 1.5 times 6, I get 9. Okay, so 3 halves is the common product. So the number 6 is called the geometric mean, but it turns out that every right triangle has these properties. So what property am I talking about? Well, I go to the right angle. I go to the right angle and I drop an altitude. An altitude is perpendicular to the opposite side. So when I drop an altitude from the right angle, I hit the hypotenuse at a right angle and it separates the triangle into 2 smaller triangles. And the small triangle there on the left is similar to the big triangle. And the second smaller triangle is also similar to the larger triangle. Why is that true? Well, triangle 2 here has this angle in it, as does the big triangle, and it has a right angle. And if I know this angle plus this angle, the final angle must be complementary to this one. So I know all 3 angles, and they'll match up to the angles in the big triangle. And the same thing is true here. In the first smaller triangle, it shares this triangle, it shares a right angle, so the last angle must be the same as the other. So with angle, angle, angle similarity, we get all 3 of these triangles are similar to each other. And then you should be able to see from that what we mean by this definition, and you can see how to prove it now because we're using this relationship, this ratio of side lengths, from the fact that they're similar. And I've color coded it to help make it simple, right? The 6 is in green because it's this value r, so that when I take 4 and divide by 6, I get 2/3. And when I take 6 and divide by 9, I also get 2/3. There will always be a number r like this, and it will always be true that right triangles have this relationship. Now, we chose it here. We chose the points on this right triangle very carefully so that the side lengths worked out nicely. If we change this, the numbers aren't going to be quite so nice, but the property is still there. Let's look at another example. So here the pattern is doubling, right? I have a side length of 2. On the left side of the altitude, double it to get to 4. That's the length of the altitude. And the other segment of the hypotenuse is 8. So 2, 4, and 8, those are 3 consecutive terms in the geometric sequence, 1, 2, 4, 8, 16, 32, 64. We can take a look at another example, and this one's tripling, right? So the hypotenuse is 10 units, but when I set this point so that its altitude will divide that hypotenuse into segments of lengths 1 and 9, then 3 will be the geometric mean because 3 times 1 gives me 3, 3 times 3 gives me 9. So that's the relationship that the Greeks were interested in. That's why they were taking a look at the geometric mean. They were understanding this relationship that is always true in every right triangle.